I'm going to note what the plans are for the week, and then we'll also go into some lessons over 4.4, 4.5, and 4.7. So it's going to be kind of packed a little bit, but I think it's kind of straightforward, and I think it should be okay. I hope you all are well. And the general plan of attack is, today I'm doing this live, and it'll probably last for close to the full class time because I'm getting a bunch of material in. But at the same time, I'm also on tomorrow and Wednesday, I'm going to leave it as office hours. So it's not going to be a teaching moment as much. The teaching will be via, I've got some recordings already up on, and As You Learn. I'll post them tonight for Tuesday that you can go in, take a look at those. I worked through a few problems, or a couple problems anyway, some from 4.4, some from 4.5, and one from 4.7. And to get the main idea about how you do the problems, the kind of questions I'll be asking on a quiz. I'm planning on having a small quiz on Thursday. So, and you guys, it's going to be critical. If some of you I said it was okay to use a DOC or DOCX last time. And when you do that, a few people sent that, and it comes up as a blank white piece of paper, a white screen to me, and not even a piece of paper, it's just a white screen. So that's not going to work with respect to being able to make an assessment or something. So you might want to practice, if you haven't done it before, to convert your files to a PDF. And that's very straightforward if you've got it as a DOC, as a Word document or something, that you can just go to print, save as PDF, as is a straight sequence, and it'll automatically make it a PDF for you. So it should be able to be done. And in order for us to do this and for it to work, you're going to have to do that when you upload the file. Okay. So that's going to be a PDF file necessity. Okay. Any other questions that have come up? I'm going to unmute you all to make sure that it's open for, okay, so by me, you're all unmuted. You have the bottom left corner, you got a microphone. It's either got a red line over it or not. And if you do, then I won't hear you if you're talking. So if you want to say something, make sure that bottom left microphone doesn't have a red slash across it, because I won't be able to hear you. Okay, if you got a question, make sure that's clear. Okay, if there's no other questions, I want to go ahead and get started and get going on the chapter 4 stuff and get moving so we can get through this stuff before this class period goes by. So again, thank you all for checking in. I'll be able to verify if you're just coming in now. A couple of you just came in. I'm recording this so you can look back after. It's going to take a little while for the system to do the recording, but before an hour is over, it should be done within the hour. An hour after class, it should be all set for you to be able to go back and listen to the recording or look at it and see what's going on. All right. So let me start into section 4.4. We did the first derivative test up to this point. I'm going to do an example in a minute that works through that too. I'll do that also. But we're mainly moving into the second half of it, which has to do with concavity. What's concave up and what's concave down. And what I'm going to do is I'm going to switch over to, I've got a webcam on my book here, and see if you can take a look. It's a little dim, but I think I've got it set up in such a way, enough light that you might be able to see that. Here's the definition of concave up and concave down. And we'll go by also what you've learned before, and the idea of what I'll say about how I've thought about it. But the way they're talking here is, if you notice, if it's concave up, if f, the function, lies above each of the tangent lines throughout AB. I'm going to draw a sketch of that just to make sure we see what that means. Concave down if the graph lies below each of the tangent lines. So let's go to my iPad, and I'm going to draw an example of that. We can see what they're talking about here. It'll take a second for it to switch over. Okay, so I hope you can see those words, concave up and concave down. And the idea is concave up, I've always kind of learned the cup is facing up, that concave up looks like that. And concave down looks like this. And that what they had, the definition they gave in the text was that if f is above all the tangent lines. So any tangent line you draw to that concave up function, notice the tangent lines are all, the graph is above all the tangent lines. That's what it was saying for concave up. And if it's concave down, the graph is below all the tangent lines that are drawn. All right. So the graph stays below it. I've never really thought of it that way, but I guess that's true. And if you need to come back to it, it's true. I've got the cup is up. And sometimes that means that even if that's the segment you've got to work with, that's a piece of the cup being up. Or if you just have this little segment over here, that is a piece of a cup that would be, if you continued on, it would be a cup facing up. That's concave up. And the same thing with down. If you've got a little thing like this, you know, that is, if you continued it, it would be concave down. Any little segment of it, you know, it's going in that direction, so that's concave down. And another thing that it's talking about also, though, the theorem that they're talking about comes into the taking the second derivative. And if I drop down, I'm going to put it back on the camera for a second to a definition that they give, a definition they give in the book. It's not a definition as much as it's a theorem that they actually state here. Let me back this up a little bit. I've got a rig going here. I've got a camera tripod that I've got this webcam tied to. And so it's going to be focusing down on the text and operating from there. But if you notice this situation here, it's talking about the second derivative. If you get down there with a function, if the second derivative is greater than 0 on the interval, then it's concave up on that interval. Wherever the second derivative is greater than 0, it is concave up. And if the second derivative is less than 0, if it's negative on the interval, then it's concave down. Okay? So that's the main idea. That's a concept, and this is being recorded so you can go back to look at it. But let's go through a problem right now. I want to go through one that I've gotten from, that I'm going to work through, and we'll go through on my iPad here. We'll actually work through the problem and use the second derivative test. I'll do the first derivative too. But what I'm going to do is get off here and go to my iPad. Again, it'll take a second to pop over. But here's my iPad. Okay, here's the function. If we've got f of x equals to x to the third minus 9x squared plus 24x plus 5. Right? And if you have questions that come up while we're moved along here, make sure you jot them down and ask me in just a little bit, okay? Here's our function. Okay, so first derivative test. Now we got a second derivative test. This question would be asking, where is this concave up and where is it concave down? On what intervals is this function concave up and concave down? So we're going to go through the process of the first derivative test we've done before, and then let's just do that kind of quickly, okay? The first derivative test. So first derivative test, we got to take the first derivative, which means we get what? 3x squared, there's 3 in front there, minus 18x plus 24. And if we factor out a 3 there, we get 3 times x squared minus 6x plus 8. All right, and that factors down, and you can see that it factors down to x and x. It's either 8 and 1 or 4 and 2, and we need 6 in the middle, so it can't be the 8 and 1. It's got to be the 4 and the 2, and the middle term's negative, so they both got to be negative, and the 8 is positive, so the product works there. So there's our factor. And now we take the derivative, set it equal to 0. We've got 0 equals 3 times x minus 4 times x minus 2. And again, this is part of what you're going to be doing quite a bit, and different functions, sometimes polynomials, sometimes other things. But right now, a simple polynomial, I think, is helpful. Gets it across. So when looking at this, this is a reminder, this 3 doesn't contribute to this being equal to 0, you know? This 3 has no effect on it. So really, it's just going to be x minus 4 equals 0 or x minus 2 equals 0. That means either x equals 4 or x equals 2. Let's do it really quickly. The first derivative test, Okay, and you remember what this function looks like. The original function up here, we've got a cubic, and the x first term is positive, so we know it's gonna, and it's got other terms involved, so we know it's gonna look something like this, right? And we've got x equals 2 and x equals 4. 2 is to the left, so 2 must be here, and 4 must be here, right? X is 4 and x is 2. And then today we're also going to talk about the point of inflection. That point, now notice this, it's where the concavity changes. And the concavity just pops into my head that I can't talk about the prison dentist anymore, though. The dentist that works on cavities, the concavities. I'm going to let that go and not say anything more about that. But the idea that the point of inflection is where the concave down changes to concave up, and that would be right in there. Let's talk about that in just a second. We'll make that clear as well. So the first derivative test, what we've done is we've got the two points, the critical points, the critical values, and we need to pick a point to the left, pick a point in the middle, and pick a point to the right. I'm going to move through this quickly because this isn't the pain, this is just review. So I plug in 1 where? I'm trying to see if the slope is positive or negative. So I got to plug it into the derivative function. So I've got to plug it into f prime of x, which is, I'm going to plug in f prime of 1 is what I'm looking at here, f prime of 1. And I'll go 1, I can plug back into the original function pretty easily. That's going to be 3 minus, not the original function, the first derivative before I factored it. I can plug in 1 there and see what the numbers are going to be real quick. I end up with this with no multiplication and that kind of stuff because it's all 1s. So that's 27 minus 18, that's equal to 9. So this is 9 plus 9, which means this is plus over here. And that means the slope is positive going in that direction here. And then if I take the derivative at 3, we get, I'm going to put this in the factorization this time. 3 minus 4 times 3 minus 2. You can see quickly that that's minus 1 times 1, and we end up with minus 3. So I end up with minus 3, which is a minus sign, which means it's the downward slope. So you can see right now at x equals 2, we got a local max going on. And let's go for the last one, f prime at 5. We're looking at x equals 5. We end up with, I'm going to plug that into the factored form again, x minus, and instead of the top, you can do it either way, but for me, this is, you can see that they're all going to be positive, so I can stop there, but this is going to be 3, 1, and 3, so that's equal to 9 again. So I get 9 plus 9, that means this is going to be plus. That means it's going to look like this. So that means, again, we got a low. That's the local min at x equals 4. Now what I want to talk about now is getting into when we're talking about the second derivative, we're talking about the second derivative being less than 0. Where is it concave up and concave down? So what we got to do here, let me go over to talking about the second derivative situation. That's true on that one moment there. Well, tell you what, let's just go through the process here. Let's take the second derivative. So if you're doing the problem yourself and when we took the first derivative, if you know you're going to be taking the second derivative, then feel free to do it right when you're, take the first one, you get 3x squared minus 18x plus 24. Feel free to take it right now and you can refer back to it or copy it down or something. We end up with here, bring the 2 down front, I got 6x minus 18, and that's equal to 6 times x minus 3. Okay, the second derivative is 6 times x minus 3. And what we're hoping to, where the derivative is negative, it's concave down, and where it's positive, it's concave up. So look with me, I want to look back at, I'm going to go to, let me go back to the book and show you the second derivative test, okay? Here's the second derivative test. Let f be a function for f prime and f double prime exist on AB. Suppose C lies in AB, between A and B, and it's a critical number of f. It's a critical number. then the critical number plugged into the second derivative, if it's less than 0, that's negative, then it's a local max. So that means if you plug it in and it's negative, that means it's concave down. That looks like what's going to happen here. Then the value, the critical number, must be a max because it's the top of that concave downness. And then the second one is if the second derivative is greater than 0, then we get a local min. So here, where it's this, we should get something that's greater than 0. So when we plug in that situation, all right? So let's take the second derivative and look at the values. So what they're saying is plug in the critical numbers. The critical numbers are a problem are 2 and 4. We got those right here. Plug in the critical numbers. So we need f double prime at 2. And we get, what is that? 12 minus 18 equals negative 6, which is negative. So at 2, notice what's happening. It's negative, which means concave down, which means it verifies that it's a local max. See, we didn't have to do that first. We didn't have to do the first derivative test to figure that out. All we had to do is take the second derivative, plug the 2 in, find out it's negative. Therefore, we know that at 2, x equals 2, we've got a local max. And then we plug in 4 into the second derivative. The other key point, when we end up with what we've got 6 times 4 minus 3, that's equal to 6. 6 times 1 is 6, and that's positive. So that means at 4, you've got this going on. So again, it wasn't a matter of having to do the first derivative test. If we could have gotten the answer just by doing the second derivative test. We could tell, and now we've got to make a determination though. It says what interval is it concave up? On what interval is it concave down? So taking the second derivative, plugging in the critical points, find out if it's positive or negative. You got it's concave down, you got it's concave up. And then one of the things I want to point back to now also is the point of inflection. We had talked about the point where it changes from concave down to concave up. So that's going to be right in between here is what's going to happen there. And notice what happened. If we had taken the second derivative and made it equal to 0 down here, if we did this up here, made it equal to 0, notice x minus 3 equals 0. That means, oops, pardon me. So if I went back to new share and went back to my iPad again, okay, so what I did was I've got so what we talked about was the fact that halfway in between the concave down and the concave up is what's called a point of inflection. So we've got this concave downness and we've got this concave upness, and where it changes from concave down to concave up is called the point of inflection. And that is going to correspond to where the second derivative is equal to 0. Notice what I did here. If I set the second derivative equal to 0, then I end up with x minus 3 equals 0, and that means x equals 3, all right? So I want to look at, so that's a situation where at x equals 3, it makes the second derivative equal to 0, so that's a thing that could be happening. Let's go to, I want to look at, go back to the text and point out, something else that we want to talk about. That is the point of inflection. If you look at this situation here, definition, first of all, let's look at, it's not a definition, but there's a theorem about the point of inflection up on top here. And it's saying that if, whoops, it's fading, isn't it? Yeah, let's stay there now. Stay there. Okay, and stay there. Okay, so we end up with, hang on one second. The tripod is not cooperating at the moment. So notice what that theorem is saying right there. Okay, it's saying that f is a function differentiable in open interval, an AB contains C, then it's an inflection point. C is an inflection point then either the second derivative equals 0 or the second derivative does not exist. So in our case, we plug in 3 into the second derivative, we get 0. Therefore, and there as a result, we can say that x equals 3, at x equals 3 is an inflection point, okay? So the second derivative being equal to 0 is the key in that situation. It's also possible doesn't exist. That's another situation. So look at the rule right underneath here. Steps for finding the inflection points. Check this out now. Notice it's saying find all numbers in the domain for which the second derivative equals 0 or the second derivative doesn't exist. Then use the test for concavity, which means check to the left or to the right and see if it's positive or negative. And if it's positive, then you've got the concavity. It's concave up. And if it's negative, it's concave down. And therefore, if it changes at the point of concavity, where the concavity changes, if it does change sign, then it is a point of concavity. So for instance, in our number 3 here, we've got x equals 3. Let me go back to that. Let's go back to my iPad and recognize that what we've got now is that at x equals 3, it makes the second derivative equal to 0. We get f double prime of 3. We get 6 times x minus 3. That makes the thing equal to 0. So that makes 3 plugged in there, right? So that's equal to 0. So that fits the situation that's a possible point of inflection. And now we just got to check the sign to the left and to the right. So, and that is by the first derivative test, we plugged in 2 and got negative. Down here, we plugged in 2 and got a negative. Plug in 4 and we got a positive. Therefore, the sign's changed. Therefore, it is a point of inflection. So you got to just check and make sure that it does change sign at that point, okay? That is concavity and determining. So the question we have to answer is, what's the interval where it's concave up, and what interval is concave down? The point of inflection, if you notice, is that changing point. So if you notice, concave down, f of x is concave down on the interval. Concave down, it's over here to the left, that's going to negative infinity, and it stops at 3. So on the interval, negative infinity to 3, it's concave down. And f of x is concave up. Where? Starting at 3, and it goes up until positive infinity up there. So on 3 to infinity. Okay? So that is getting through the idea of, we worked through the first derivative test that was a review. Then we went through the second derivative test, which meant the second derivative test says, is it a max or is it a min? So to be honest, the second derivative test let us know this is negative. So the answer for the second derivative test, if you look back on what the second derivative test said, is that f prime of 2 is a local a local max. It's concave down, it's negative. Therefore, it's a local max. Local max there. And this down here, at 4, we've got it's positive. Therefore, this is a local min. So with the first derivative test and second derivative test, you're determining if it's a local max or a local min, okay? So that is the situation we did that with that function, all right? That's 4.4. Are there any questions that have come up regarding that problem, that sequence? Feel free to speak up. Okay, so what I'd like to do kind of quickly is move into, if you don't mind, move into section 4.5. There's problems in Sapling that are regarding that using the second derivative test, first derivative test, etc. And now I'm going to work through a problem that has to do with L'Hopital's rule, section 4.5. Okay, need to keep moving. So if you got questions ever, speak up, but I'm going to keep moving through here. So what we're looking at here is, first of all, there's a term called the indeterminate form. There's times when you take limits of functions, limits of polynomials, but in this case, we're talking about taking a limit of a rational function and determining that you've got an indeterminate form. The outcome turns into one kind of or another. Let me show this. I'm going to go back to the text here. Okay, so what I'm going to do is backpedal here a little bit and crank back. So you can see the whole thing. Okay, so the indeterminate form of C of the type 0 over 0 or infinity over infinity. So if you plug in, if you take the limit as x is going to C of some function, see this situation here, and when you do it, you get the type, you get 0 on the top and 0 on the bottom. You get plug it into the top, C into the top, you get a 0, and on the bottom you get a 0. Then it's of the type 0 over 0, and that means f of x becomes 0 and g of x both become 0. That's going to determine whether we're going to use, that allows you to use L'Hopital's rule. And also of the indeterminate form infinity over infinity, it's a little different, and that is that when you plug in the C, the limit as x goes to C of the function, you get positive or negative infinity on top, and you get positive or negative infinity on the bottom. So that is the situation. That's an indeterminate form also where you can use L'Hopital's rule. And now comes the point where, what's L'Hopital's rule? Well, let's go back and apply ourselves toward it. The situation is that I'm going to go to my iPad now. And there's a couple of examples here that utilize it. I'm going to get L'Hopital's rule up on the screen in just a second. And to me, L'Hopital's rule wasn't a real obvious statement. The way it's worded, it seems reversed a little bit, but it is what it is. It's L'Hopital's rule. And so what I want to look at here, let's just look at it for a second, and we'll come back. And I want to go back to the book and point this out. Let's see. I want to go specifically to this. Okay, so here's L'Hopital's rule. There's the theorem, that's L'Hopital's rule. And it says, the gist of it is this, that if you've got a function over a function, f over g, and c doesn't cause g to become 0, all right? If when the limit as x goes to c, if it turns out to go to a particular value that's indeterminate, 0 over 0 or infinity over infinity, then whatever the limit, true limit is, if you take the derivative of the top, you take the derivative of the bottom, and you take the limit of that new rational function, that limit is the same as it was for the original function. So this is saying that if you've got a function and this goes, it's this, if you plug in C and you get 0 over 0 or infinity over infinity, take the derivative of f here and take derivative of g here, plug in C, and that is also the same limit. It takes you to the same limit. So that's a shortcut form if you run into a problem with that. And let me do a problem. I'll do a problem right now on my iPad that does that. So let's do this. I'm going to the iPad now. And the first example I'm thinking of doing is if we have the limit as x goes to 2 of x squared minus 4 over x minus 2. Okay? So you can see one of the first things you'll need to do whenever doing a problem like this, where you're trying to use L'Hopital's rule or whatever you ask to do it, is plug the value in and see if you get 0 over 0 or infinity over infinity first. Demonstrate that you get that. As x goes to 2, you plug it in. You could probably do it up here, you know? Just you could do it up here and show me that that's 4 minus 4 over 2 minus 2, which is 0 over 0. Check. That verifies that you can use L'Hopital's rule. L'Hopital's rule needs it to be 0 over 0 or infinity over infinity. So what we'll do is use L'Hopital's rule, and that means we'll take the limit this time as x goes to 2 of the derivative of the top. Derivative of x squared minus 4 is 2x. And the derivative of the bottom, derivative of x, is 1. And that means, well, we can plug, it's the same as this limit, okay? The limit as x goes to 2 of 2x over 1. And 2x over 1, that is equal to 2 times 2, which is 4. So that is using L'Hopital's rule. We took the derivative of the top and derivative of the bottom. Notice what we could have also done in this problem up here, though. If you had started with limit as x goes to 2 of x squared minus 4 over x minus 2, you guys, something really important too that some people get a little slack on. The limit here, this notation, is a crucial part of the correct solution of the problem. Notice the limit as x goes to 2 of this is not equal to 2x. The limit is an essential part of answering that question. We had to get the 2 in there, so the limit was needed in order to do that. But then once we plugged the 2 in, we didn't need limit here, okay? But what we could have done also in solving that problem is equal to the limit as x goes to 2. We could have factored the top, x plus 2, x minus 2, over x minus 2, and see these cancel. And that would have also given us, that is the limit as x goes to 2, x goes to 2 of x plus 2, and that equals 2 plus 2, which also gives you 4. You get 4 either way. There's going to be several problems, though, where you can't factor it, you can't clean it up and get the answer another way. So what you need to do is recognize L'Hopital's rule. This was 0 over 0. Therefore, I could take the derivative of the top, derivative of the bottom, and get the answer from there. Okay, let's do another one where it's not quite so obvious, okay? Let's go to the limit as x goes to 0. Any questions on that before I go on? Unmute your mic if you're asking. I can't hear anything right now, so if you've got something, let me know. Okay, here's another one that can't be factored quite so nicely. And we've got this. So the limit as x goes to 0 of e to the 2x minus 1 over x. And so first step would be show that when you plug in 0, you get 0 over 0 or infinity over infinity. So I get e to the 0 minus 1 over 0, which is 1 minus 1 over 0, which is 0 over 0. Check. That qualifies as a L'Hopital's rule kind of moment. So I meant to do it up a little higher. I didn't give myself enough room. But now what I'm going to do is go ahead and use L'Hopital's rule. That means I can take the derivative, make it equivalent to this new limit. That's a little simpler, and see if it cleans it up in a way that we can plug in our 0. So we got to take the derivative of the top and the derivative of the bottom. This is not the quotient rule. You take the derivative of the top and the derivative of the bottom. Derivative of the bottom is obvious. Derivative of x is 1. Derivative of the top. Okay, you got to use the chain rule. This is e to the u. E to the u minus 1. So the minus 1, that derivative, that's 0. But the derivative of e to the 2x is e to the u times the derivative of u, which is 2, right? So I could put that 2 in front. Same thing here. Okay, now if you notice, if I plug in 0 for x, take the limit, plug it in for 0, I get 2 e to the 0 over 1, which is 2 over 1, which is 2. All right, so the idea of just being able to take the derivative of the top, derivative of the bottom, and verify that you do get 0 over 0 first, and then take the derivative of the top, derivative of the bottom, plug it in now, and see if it works. Got it. Let's do one more that shows that it's a multi-step process also, if it is necessary. If it happens more than once, you got to follow through. So if I have the limit as x goes to infinity this time, let me do that one. Tell you what, let's first do x over e to the x. This is our first infinity situation. So look what happens here. Now remember, the idea is you don't really plug infinity in. Infinity is not a number. but you get the indeterminate form where that top number is going to infinity and that bottom number is going to infinity, right? Therefore, it fits L'Hopital's rule. So I can use L'Hopital's rule on it, which means take the derivative of the top. Now you still need that limit symbol. The derivative of the top, derivative of x is 1. Derivative of e to the x is e to the x. And now as x goes to infinity, I get infinity on the bottom, and as that's getting huge and we stay on 1 on top, that's going to 0. So the final answer turns out to be 0 in that case, all right? Using L'Hopital's rule. Now, let's do one more example with that, but this time, watch if it had been x squared on top. Okay, so if I plug it in, I get infinity over infinity. So that means I can use L'Hopital's rule, check. Okay, so that gives me, therefore I can take the derivative of the top over the derivative of the bottom and try this now. Okay, notice I still get infinity over infinity. So I get infinity over infinity, which means I can use L'Hopital's rule, so you do it again and just use it again. And therefore the derivative of this, I still need lim of x goes to infinity. Now we get 2 over e to the x. And now the limit as x goes to infinity of this, we get 2 over, that's going to infinity on the bottom. So this ends up being, again, the bottom's getting huge. We got something on top that's going to 0. Okay, this is going to infinity. So the huge number on the bottom, that takes it smaller and smaller and smaller and smaller, it's going to 0. Okay, and notice it's twice as big as this one, but it's still going to 0. This is twice as big as this, but they're both going to 0. That's kind of special. All right, and therefore, I just wanted to show you that you could have to do it more than one time in the situation. So that holds true for 0 over 0 or infinity over infinity. Hey, you guys, listen, I'm going to step for a second. I need to go back and extend the time. I was set it up to stop at 45, and we might be here till then. So I'm going to go back to our class and change the end time to end at 50 and make this a 60-minute meeting instead. Because we started 10 minutes early is the idea. And I just wanted to make sure it didn't cut us off while I was in the middle of conversation. So now I'm going to go back to us. Okay, so any questions on the L'Hopital stuff at all? Feel free to ask. It's fairly straightforward, but get in and do several of the problems, try them and see if questions come up. They should be straightforward. And again, you guys, remember, don't use up all your tries. Make sure you can try it with me, get on it with me on Tuesday and Wednesday. We're gonna be getting together for office hours, your option, during class time, and then from 2 to 3 also I'll be available for office hours, okay? All right, that's it for 4-5. No questions? Okay, let's go to 4-7. I've got a simple basic scenario I wanna do for 4-7, and that is contending with optimization problems. This is kind of the cool part of taking the derivatives and using the rules we've just learned to actually solve life stuff, problems, and go from there. So what I want to do first of all is show you an example of what an optimization problem might be. And let me move this out and move this in, and I'll show you just a couple problems. It came from a different text. It's a simple problem that it's very straightforward, I think, to see this. If you work from this, it'll be a little more obvious, I think. So what I want to do is share screen and go to the book, which is right there. Okay, so here are 2 problems that show the numbers 1 and number 2 here are examples. And I'd like to work through particularly number 1 right now. We can do number 2 tomorrow or something like that kind of line. It's a variation on the theme. But look at number 1 there. the sum of two non-negative numbers is 100. What's the max value of the product of these two numbers? Okay, so look at look what's going on there. The circumstance is there's two equations needed. There's a sum equation and a product equation, all right? One of them you're trying to maximize the product. So we've got a sum equation to 100, and then we're trying to maximize a product. And therefore, notice we're given a value for the first one. We're given a constraint to work with. And so I'm going to switch back to iPad right now. So check it out. Notice the situation. The sum is 100, maximize the product. So what I'm going to do is go back to the iPad and write down what that problem was saying. So there's two equations that we had to get out of this. We had to write the sum equals of two numbers. So that's going to be x plus y is what I'm going to choose for basic numbers. And then we've got a product, which equals product, or you could write that out, or equals x times y. All right, two equations. You're told what the sum is. There's a constraint. So we've got 100, and you might want to call this S. You know, you could call that, let me clear that off. Simplify it down to a letter, a variable. S equals x plus y. That S can look like a 5, so that's not really a good number to use. But we're now told that there's a constraint on this. So we've got equals x plus y. And then we've got the other problem, and so I'm going to use the letter P to equal x times y. And now by using that first problem, we can get this. The problem is we want to maximize it, which means we want to take a derivative and set it equal to 0. But the situation is that we've got it in terms of x and y. So we need to get rid of one of the variables. And if you've got a constraint on the other function, then what you can do is solve for one of the letters, substitute it in the other, and it'll just be in terms of, for instance, x. So if I solve for y here, I end up getting, I have to subtract x, I get 100 minus x. Therefore now, if I substitute that into here, I get that p equals x times 100 minus x, which is equal to 100x minus x squared. So I get this new function, and this now is just in terms of x. Okay? So I could write it like that. P of x is equal to 100x minus x squared. Now I can take the derivative of this in terms of x, and we can solve from there. So let me just kind of move through that and do that, and watch the process. You can look back on this if this is moving too quickly, but the idea is I need to take the derivative, set it equal to 0. Notice what the shape of this graph is. It's a parabola, upside down. Means it's got to have a max, and the max is going to happen where the slope is equal to 0. So take the derivative of p, right? Set it equal to 0. Solve for x. Okay, we got the x. So sometimes you get to the problem and you go, yes, I got x, I'm done. No, you're not done. The question was, what's the maximize the product? What is the maximum product you can get? That means you need to go back to this equation. First, you need to go back to this equation, but we've got x is 50, but we need y. Notice we've got y solved here. You could go back to this function right here, just plug it in there. You could just plug it in. You could just plug it in here into this function. But I've already started toward the process. So let's figure out what y is first. That's sometimes a valuable piece of information to know. Well, we know that y equals 100 minus x minus 50. So y equals 50. So y equals 50 and x equals 50. Therefore, the final answer is the product, max product, is equal to, max product is equal to 50 times 50, which is 2,500. So make sure you go back and answer the question. So the maximum product, it probably would have been good for me to just leave this P back here. You know, leave this P. Max P equals 5550. And therefore, for the final answer, the maximum product is 2500. Okay? And the second question has to do with, it gives you the product information instead. You might want to try that yourself if you can look back on the problem and try it. But any questions on that problem? Notice the sequence of events. You had two functions. You were given the constraint of one. One of them set to a value. You want to maximize or minimize the other. All right? So that means this is the one you want to maximize. That means you want to get it all in terms of x. So if I solve for y in the other function, plug that into the function here, I end up with a function that's totally in terms of x. Take the derivative, set it equal to 0, solve for x, plug it back in, solve for y, or calculate the p-value you're looking for. Sometimes you're going to need to know what the other number is, so plugging back in and figuring out what y is. Remember, you did solve for y in the process of solving this problem. You could figure it, but the question was just saying, what's the maximum product? So you could have gone back to this question right here and plugged 50 into p of 50 is equal to 100 times 50 minus 50 squared, which is 5,000 minus 2,500, which is 2,500. And you get that either way. So max P equals 2,500, either way. Okay? So work on the problems in Sapling. I gave a handful, probably 10, I think, from 4.4 that you can go back over. You can go back over the first derivative test, second derivative test, point of inflection, get those things down comfortable. And then 4.5 is L'Hopital's rule. And then the last set is, or the optimization problems are doing this right here, are 4.7. Okay? If you've got any questions, feel free. I'll be online again at between 2 and 3 today. And I'll also be online at 2 and 3 office hour. We got office hours during class time tomorrow and during 2 to 3. But then on Wednesday, and then the situation is we're planning to have a quiz on Thursday. All right, that's the idea of some of the basic questions of some of this stuff that we've just been doing. Okay, questions at all now? You're welcome to stay on if you want to. I'll be here for another minute and a half. Otherwise, you can feel free to go and check in during office hours if you want, or not, on Tuesday and Wednesday, and just be ready for a quiz. We'll do. I'll get some communication to you by the time before we take the quiz on Thursday. Okay. Do well. Yeah.
I have a question.
Go. Who? We got Holly?
Yes.
Yeah, go ahead.
Why on the optimization problems, why does finding the derivative help you get to the final answer?
Okay, so notice the situation that you're trying to maximize one of the equations. And in this problem, notice the situation was that, let me pull the iPad back up. And I hope if I time out, I think if you stay on, we should be okay. Okay, I'm gonna go to
Okay.
I'm gonna go to my iPad. Okay, it'll just take a second to pop up.
You're good.
Okay, so we noticed that that the second equation, when we did the substitution, we end up here with the product is just in terms of x.
Right.
And this function, which is said we're trying to maximize, look at the shape of it. It's a parabola.
Okay.
Upside down.
Mm-hmm.
It's going to happen where the maximum occurs.
Okay.
So the answer to this question is, where is the slope equal to 0? The slope of the tangent is equal. That's
yeah.
max, you know?
Okay, that makes more sense.
And so that's typically going to be this. That's why taking the derivative set and equal to 0, you get the max, you get the min, and that's where those kind of questions are being answered, you know?
Okay. Thank you.
Good, thanks for asking. Good.
Yeah.
And so, anything else at all?
No, I think I'm good. Thank you.
Okay, keep a smile going.
Sounds good.
All
Bye.
right, all right, you got a thought?
No, I was just
Listening?
hey?
Just listening to hear about
Yeah, I was just listening. Just curious.
Hope you're doing okay.
All right, thank you. You too.
Okay, good. And see you sometime later this week.
All righty.
Be well.
Yeah.